Alright, last problem. And I'm only going to do part A because part B, I'm not really concerned with that concept. So damped motion, let me just write down the equation. X of t equals xm uh, e to the negative b t divided by 2m. Alright, so first off, um, when t is 0, e to the 0 is 1, and so at time t equals 0, before there's been any time for damping to take place. By the way, damping is like friction in a sense. It's when energy is sort of sucked out of a system, an oscillating system, and so it doesn't oscillate at the same amplitude. It's like when you have something swinging back and forth, but then over time it doesn't. Let me try redrawing that. You have something like swinging, so it starts up here, and then on the way back it doesn't quite go as high, and then on the way back it doesn't go quite as high, and eventually it's like, and then it stops, right? So that's damping. Energy is pulled out of the system. So when t is 0, there hasn't been enough time yet, or any time for damping, so this equals 1, and so the x position is equal to the amplitude. But as t gets bigger, e to the negative bigger number gets smaller and smaller, and it's a fraction less than 1, and so the x amplitude diminishes. It's a percentage, a decreasing percentage of the original amplitude as time goes on. So for 57, we want to figure out how long it would take until the resulting oscillation right here is 1/3 of the initial. So we want to know when x of t is 1/3 xm. So we'll just plug that in here. 1/3 xm equals xm e to the negative bt over 2m. xm's cancel. So 1/3 equals e to the negative. Now they give us b, don't they? Yeah, it's 230, although it's in grams. We could convert that to kilograms, so it's actually 0.23, 0.23 times, times t divided by 2, and then the mass is 1.5. 2 times 1.5. And so we're solving for t. To get rid of the e, we got to do the ln of both sides. So just ln this, and that cancels. So ln, whoops. One-third equals negative 0.23t over 2 times 1.5. Solve for t, and you get t equals 14.33 seconds. So, we could figure out how many oscillations. In fact, that's what that's what part B is asking. How many oscillations in that time? So, it'll swing back a few times for this amount of time, and obviously a period is going to be less. Well, not obviously, but most likely a period is going to be less than 14 seconds, and so it's going to oscillate back and forth a few times before it reaches 1/3 of its original amplitude. So yeah, but we're not going to do that because we don't need to. Okay, so that's all the videos, all the sample problem videos for chapter 15. That's the last sample problem video of the year. Happy New Year, and goodbye.